I think without further ado, let's put our hands together, and I think it's going to be a really exciting talk. Thank you.
Brilliant. Thanks, Tom. Really good to be here. So, before we get started, I just wanted to tell you all what we're going to talk about today, so you know what's coming. So first off, I'll talk a little bit about myself. I know there was some interest, Tom said, just for like the path I'd taken through my career because of coming out of this master's program and stuff, and it's interesting for other people, so I'll talk a little bit about that. Then I'll talk briefly about the history of generative music in general, just a real kind of like zoomed out view to kind of set the context for stuff that's going on now. Then I will talk about the more recent history of machine learning and AI techniques for generating musical audio directly, and also give a kind of like broad overview of the kind of techniques that are used in that domain. Then, if there's time, I'll go through some of my recent research, including some like very, very recent stuff that's coming out today. And if we get time, then I'll talk a little bit about what I think is important for the future. Is the mic rumbling? Okay, right. I thought that was me. Good call. Okay, so first off, me. Tom already touched on, I guess, the high-level details, but I guess you might think that it's a bit of a weird career path to take. So I started out thinking about physics, ended up doing AI, and went through many things in between. I guess I would say that like the transition between these kind of different disciplines always didn't seem like a big deal at the time. Like there was always something overlapping. So I came to Edinburgh initially as kind of like a lost physics student who liked doing physics but also liked music and wanted to do something a bit cooler than just like, I don't know, solid state physics or like the normal stuff. And I found this place, which was, and still is, weirdly a course designed exactly for that strange niche of people from physics who want to do stuff to do with music. So I ended up here, got into doing physical modeling stuff with Stefan. Initially physical, like electromechanical things, then later got into doing electrical things as well. And that leads you into DSP. So after my PhD, I kind of made my career on DSP for 5 or 6 years at Native Instruments, making plugins, making like audio effects for musicians to use to process sound. And then around halfway through my time there, so I think we're talking like 2016, I could see the way the world was going in terms of like machine learning and like new techniques emerging. So we set up a new team at NI to basically apply that stuff to the kind of problems that we had in our music tech products. And what that ended up being in terms of the public, has the picture gone? There we go. I think I knocked it, so that's my bad. We set up this new team to apply machine learning to the kind of problems we faced in the music tech domain. Initially, that was things like virtual analog modeling, which there's a bunch of people here doing here as well, like Alistair and Alec. We also did a lot of work that never became public on generative modeling of audio for musical uses, so samples and loops and things like that. So I had done quite a lot of work on that, and then times changed. It's time to go somewhere new. Like 2022, I believe it was, I left Native Instruments to go to TikTok, who had a team in London doing symbolic generation of music, and they wanted someone to like start their generative modeling of musical audio work. I spent around just over a year there doing that, and I'll talk about some of the work I did there. And then around the end of last year, I switched from there to Stability AI to carry on doing that at not a bigger scale, similar scale, smaller scale of company, great team, and that's what I do now. So if I was going to think about like one single theme that unites all of my work. It's all about processing or generating musical sound for creative uses, using whatever technique. So it can be DSP, it can be machine learning and AI latterly, but it's all around making stuff that lets musicians produce or manipulate things in interesting ways. By the way, jump in anybody if you want to ask a question. Like that's it, I'm cool with like doing it in discussion style rather than saving them all to the end. Okay, so now a little bit of preamble to set the scene. So the point I want to make is that there's been a lot of hype around generative music in like the last 2 or 3 years, but it's not something that's particularly new. So you could say that it's been around since classical antiquity, basically. So, for example, there's these instruments called Aeolian harps. I was trying to work out where exactly they originated. Some people say in Greek times, some people say it's like a 16th century thing. Anyway, early generative music technique. Let me play you a little excerpt from an Aeolian harp so you get an idea of what that is. So it's basically like a harp instrument that's played by the wind. So the notes appear, I mean, I guess you could consider it random, but randomness is like the first step towards something generative, right? So, and they sound like drones, so like this. So very interesting, atmospheric, more abstract instruments. That video, by the way, I've just noticed is from Rod Selfridge, who some of you might know, because he's been around this department a little bit, I think. Yeah, also early examples of generative techniques in music. I mean, there's reports of people like Mozart and Beethoven playing dice games to decide like parts of their musical compositions, things like this. Then in the 20th century, you have people like integrating this stuff more kind of formally into their composition techniques. So people like Xenakis, Ligeti, Milton Babbitt. I'm going to play a little excerpt from a piece by Xenakis. So he's very much, again, on the kind of random side of generative, I would say. Like he was embracing like the stochasticity and things like this, and producing very interesting music with it. It's a great piece, you should listen to it, I would recommend it, but we won't listen to it all now. So I think that there was a shift around the end of the 20th century. So up until that time, you could say that most of the interest or most of the application of these generative techniques were in like art music, so more kind of like highbrow or avant-garde stuff. But at the end of the 20th century, people started thinking about these techniques in popular music, but also building systems that could be used commercially to like provide things that people want through these generative processes. So, I mean, another example of that is Brian Eno. I think he did some work with a piece of software called Cone, which I can show a brief video of. So this is late 90s, so Windows 95 stuff. You can see there's an abrupt transition here. So this doesn't sound like art music anymore. This is a shift in the landscape, I would say. This was used for more like functional applications.
Now we're not going to listen to all of the piece. We'll notice a few things about Con Pro. Here is the timeline for the piece itself. As you can see, we're incrementing in time here along this line. We have volume envelopes that each map to specific.
Well, again, we won't listen to it all, but you get the idea. So it was basically some software that allowed you to generate MIDI notes that you could then synthesize with whatever you want. And through that, you could do art music with it. You could also mass produce like stock music, whatever you like. So moving into the 21st century, I'd say, maybe even starting in the late 2000s and till quite recently, the big focus in generative music was starting to apply some techniques from things like machine learning, but to symbolic generation. More kind of traditional machine learning rather than deep learning, usually. But that became the trend. There was quite a few startups in the space. There was one called Duke Deck, who actually turned into the team that I joined at TikTok. There was another company called Amper. There's lots of them. I mean, an interesting thing is that most of those companies got acquired by stock music people, and a lot of the content from those symbolic generative models are now in stock music libraries that people are now using to train generative models that work on audio, on the audio level. So there's kind of some recursion going on there. Yeah, maybe this is only in my own bubble, but I feel like there was a big explosion in interest in generative music in the mid-2010s as well, as people, as part of the modular synthesizer boom. It almost became a cliche that people would buy an expensive synthesizer and then use it to make generative ambient music that they would post on YouTube with a nice video with a house plant. I'll give you a short example of that. It's a guy called Lightbath who does this very nicely. Oh, YouTube, you've let me down. Okay, I'm not gonna challenge that. Anyway, so the point of this preamble was just that this is not a new topic, right? So we're doing this directly in the audio domain now, but the idea of generating music is something that is old, very, very old indeed. Yeah, and what's happening now is more the culmination of that rather than anything particularly new. Okay, so now on to the next section, what's been going on recently, specifically in generating musical audio with machine learning techniques. So I want to give you a quick history first of just what happened before the big explosion of work in this area. So as far as I'm aware, the very first paper that tried to generate musical audio using deep learning techniques, directly in the audio domain, was WaveNet. I was speaking to some of my colleagues. They were saying they think sample RNN was first, but just was published slightly later. Anyway, those are basically the two kind of papers that came first. WaveNet was coming out of Google DeepMind. Sample RNN, I don't remember. They were very interesting techniques. So both of them were slightly different formulations of modeling just a raw audio waveform, one sample at a time using an autoregressive model. And I can play you what they sounded like. So these models at this point were mainly trained in an unconditional mode, so you wouldn't necessarily give the model any information about what you were trying to generate. You would just train it on a bunch of piano recordings, and then it would produce piano recordings. So there's not really any control apart from what you put into the training. And piano music from WaveNet sounded like this. So actually not that bad. This was mind-blowing at the time for a lot of people, me included, I think. I mean, WaveNet was very compute intensive, so you couldn't generate large amounts of audio. Also, it didn't really hold kind of long-term coherence. So you can hear that piano music sounded kind of great in a 10-second segment, but if you generated a minute, then there would be no larger structure really. It would just be babbling. But it worked. So that was kind of a sea change in that world. Sample RNN was doing similar things at the same time, like I mentioned. I want to play you actually quickly. So my colleagues in my current job, DataBots, they were very early people working in this domain. They trained a sample RNN model on a library of death metal that they built up. And they have had a live stream, an infinite live stream of this playing for the last, it says 2019, right? So that's the last 5 to 6 years. Yeah, and it sounds like death metal. I'll play 20 seconds or something. So it works in the broad sense. And again, you can hear the same thing. So again, that in the microcosm, it sounds like if you listen to a small snippet, it sounds like it's metal. But it doesn't have any of the long-term structure of that. It's just babbling. It just sounds coherent locally, but like over a longer time period, it's nothing. So over the following years, people started applying new generative techniques, or generative techniques that were established in other domains, for example, GANs, to this kind of waveform generation problem. You also had people starting to apply similar processes to spectrograms. So tachotron, for example, is an early example of that, basically making a generative model by generating an STFT, like frame by frame. That was more for speech than music, but still, it's interesting. And then we get into like 2020, which is where the kind of foundations of the current explosion started to be laid. So in 2020, Jukebox came out from OpenAI. I feel like it's a little bit forgotten, which is weird because OpenAI is so like huge. But they actually had a model that did this stuff very, very early on. So the big change in Jukebox, also in Rave actually, which I've listed here, is that they started shifting away from modeling the audio like directly as a waveform to modeling it in some kind of latent representation instead. So we'll talk a bit more about latent representations in a bit, but basically that's some kind of like abstract representation that contains or a large part of the information that's in the raw audio waveform, but is maybe compressed on the time dimension or like in a higher dimensional space, whatever, just something that makes it more expressive, essentially. Another important thing that happened in 2020 is that people started using diffusion models to generate audio directly in the waveform domain. So that brings us to 2020. At that point, with the exception of Jukebox maybe, which could produce interesting coherent music, albeit low audio quality, up until that time, generating musical audio directly had been kind of like a novelty problem. Like it's something that you would show that your model could do as like an extra, as an extra flex. But it wasn't really good enough or controllable enough to do anything meaningful with. I'd say that really changed in 2023, but the things that allowed that to change happened a couple of years previously to that, so I want to talk about those first. And basically, the two big switches that happened were there was a lot of progress in, and I'll talk about this a little bit more again, models that would compress raw waveforms or raw spectrograms into one of these abstract representations. So SoundStream is a really prominent example of this. Also Encodec, which is a variant of SoundStream that was published by Meta. So these models and the audio quality and the kind of compression they were able to provide, also like changing from potentially the continuous domain into like a tokenized discrete domain. This is what allowed people to start taking like successful generative modeling techniques from other domains and start applying them to music in a sensible way, or applying them to musical audio. Because before that, music had very different properties to, for example, text. Like 1 second of audio, like high quality audio is like 44,100 samples, right? That's way bigger than, well, okay, not now, but that's way bigger than people were addressing in the text domain at the time, for example. Now, maybe not, but still. Anyway, so these codecs basically allowed people to put the audio into a format that then they could use in these models. So that was very, very important. Also, people started experimenting with these contrastive models for connecting modalities. So you had initially a model called CLIP, which was basically a model that was trained to produce representations that were common between text and pictures. So you basically train this model, has two like network structures. You put in a text description of some image in one input, you put in an image in another input, and then you train it so the representation it has at the other end is close for those two things. And then things that are not the same, so if you have the wrong piece of text and a different image, those representations are trained to be distant. And from this you can learn a representation that encodes like the common semantic meaning between the text and the audio. So it's in a way more powerful than just a text embedding on its own, because it encodes things that you know about the sound. And the combination of these two things are basically what led to the explosion of music models in 2023 and beyond. The first big one to hit the mainstream was MusicLM from Google. So that was basically an extension of a previous model that they'd published called AudioLM, which was basically, it was a general audio model / speech model that came about from encoding a bunch of audio using one of these tokenizers, one of these codec models, and then just treating it like it's language, like just pumping it into a transformer and predicting the next thing that's going to come along. So, I mean, there's more details to the model, but that's the high level view. So MusicLM appeared in 2023, blew everybody's minds a little bit because it could do properly text conditioned music generation. And we can hear what it sounded like at that point. Let me pick one of these at random. Okay, I've played this one before, so let's go there. So you can see with, like, this was again kind of mind-blowing because, okay, audio quality isn't that great yet. Like, it's not hi-fi, but it's following what the prompt says, and it's producing things that are at least broadly musical. So that was kind of a sea change moment, I would say. Hot on the heels of that came MusicGen from Meta, which is kind of a different take on a similar language model style way of modeling musical audio. That sounded a bit better than MusicLM already and was able to generate more efficiently because it had shorter sequences. We can hear a little bit of that. So this is from, actually maybe we can find one that's similar to, okay, no, they don't have the same prompt. That's a shame. So MusicGen sounded like this. So again, a bit better, slightly higher audio quality, the musical coherence was better, generation speed is better, etc., etc. And then coming into the end of 2023, which is only last year, it's crazy to think, we had other big things appearing. So Stable Audio from the company that I'm working for at the moment, as well as Suno, which is getting a lot of hype at the moment. And then at the beginning of this year, also Udio, which is a similar platform to Suno for generating lyrics conditioned music. So yeah, this brings us to the current day. So we've gone from this stuff being kind of not really workable for like anything serious to, I'd say we're on the cusp of it being serious now. Like some stuff is good enough to be used in real production. I mean, you can hear great songs out of Suno, for example, or from some of our models. So we're just reaching that point now where this stuff is seriously useful and starting to be possible to apply in like workflows that aren't concentrating on the artifacts and like being more avant-garde or whatever. So, yeah, now I wanted to zoom out a bit and talk a little bit about the techniques involved. So this was the history of like how we got to where we are now. But yeah, some of these elements probably bear a bit more explanation. So a big one for me is, and I talked about it a little bit already, is this idea of not working on raw audio. So not working on raw data, but instead putting it into a different space that it's easier for modeling techniques to engage with. And we do this usually, but not always, with a setup that is broadly an autoencoder. So if you studied any kind of machine learning, you'll know what an autoencoder is. It's basically something that has an input and it has an output, and in the middle you have a compressed representation that contains less information that you had at the input and the output, and then it's just trained to try and make the output the same as the input in the broad sense. And by doing this, you try and discover like a compressed representation that, well, hopefully has a number of properties. So it should usually, and it usually kind of works out this way almost by accident, it should maybe contain more semantic information about the, like more high level information about the audio than the actual raw audio did, so there's less redundancy. Because when you compress something down to be very, very small, you kind of, the information you have to store has to be more zoomed out, and then you worry about like the coding part of the model to turn that back into audio. The other big thing is that generally you would train these models to compress things in the temporal dimension. So I touched on that already. So 44.1 kilohertz, like audio samples, that's not something that you would generally want to run a machine learning model on directly. When you compress stuff with an autoencoder, you're often compressing it in the temporal dimension by maybe 2,000 times or 1,000 times. I mean, actually, normally 1024 or 2048 because we like powers of 2, right? But yeah, basically compacting things down a lot. And also probably projecting them into a higher dimensional space to then pick up a little bit of the slack and allow each temporal step to contain more information than it did in the original. So there's a couple of different variations of models like this. Some are designed to produce what are called continuous latent vectors. So that's basically like each time step would be described by like 64 float values or something like that. So that's existing in a continuous space. A lot of models also apply a process on top of this called vector quantization, which takes that continuous representation and turns it into just a series of integers describing each step. So you might, one step might have like 5, 7, 22 or whatever. And these, the vector quantization process basically learns how to assign these integers to essentially important spots in the original continuous space, and then how to apply corrections on top of these important spots to get to a pretty accurate value. So by applying this quantization process, you can end up with an even more compressed representation. So you don't have like the 64 floats anymore. You have just a stream of integers. And that was a very powerful idea, like I mentioned before, because then that allows you to start treating things in the same way that language is treated, the same way that we treat text. So we can start applying methods from that domain. So, yeah, and I made these on the train, actually. I wanted to do this for a while. I wanted to go also through quickly for the people who haven't come across this stuff before, like the broad kind of modeling approaches we see in this area. So once you've turned your raw audio data into like this stream of latent representations, like how do you turn that into something that can generate new music, basically? And you would take one of several approaches that are kind of standard from other parts of AI and machine learning. The big dominant one, I suppose, is the autoregressive approach, or sometimes called next token prediction. And that basically means that you train a model to look at the past and then predict one step in the future. And then when it's predicted that one step in the future, you put that back into the context for it to look at again, and it predicts the next one, which ends up looking like this. So we're just filling in the blanks as we go. And the interesting thing about these models is that they're causal, so they only see into the past, they don't see into the future, which is both an advantage and a disadvantage, depending on what you're trying to do. So another interesting and maybe less prominent modeling method is masked modeling. So that's also something that comes originally from the language domain, although usually more for building representations rather than like specifically generative models, but it has been used for that and is used that way in audio as well. So in masked modeling, it's very much like the autoregressive approach, except instead of predicting the next token based on the past, you just delete little bits of your sequence. So again, you can see these gray elements are meant to represent the bits that have been deleted. And then you just train the model to fill in the blanks. So you give the model the information that you have left there and say, what do you think is happening in these gaps? And through that way, you can build up a generative model that can iteratively fill in gaps and build up a complete sequence in that way, which looks like this. There we go, filling in the gaps. Nice. So the final prominent approach is what I would call iterative refinement. I would say diffusion, which is a really popular modeling technique, is the most prominent example of this, but there are other variations that are doing similar things, like in the same broad zone. So with these techniques, you start out with like a random sequence, basically. So you want to generate your 5 minutes of audio. You start out with 5 minutes of noise, essentially. And then you train a model that is able to like iteratively refine that noise into an example of the thing that you want to generate. I won't go into the details of how you actually do that because it's quite complicated. You can even like think about it in terms of differential equations and stuff, which is good for some people in this room, but yeah, it's too much for now. But yeah, this is another prominent approach. And we can see what that looks like here. So you're going from noise into something meaningful over many steps. So yeah, I would say there's kind of a little bit of a taxonomy of models going on. So like people often think, oh, it's diffusion, or oh, it's like a language model. Really, that isn't the way it works though. Like I'd say you have two different things going on. You have the type of data that you're working on. So that could be raw data, that could be one of these latent representations in continuous form or discrete form. And then you have these different ways of modeling them. And you can mix and match these basically. Like you can have an autoregressive model that's working on continuous latents. You can have an autoregressive model that works on discrete latents. All of these are just like different views on the same kind of two axes. Cool. And so, okay, what are the open challenges in this domain, and like what, well, at least as of like the end of 2023. Well, a big one was that most models for generating music in the audio domain were trained only on 10 seconds to 30 seconds. So I talked about this a bit already. They were only producing output that is locally coherent, but not like a full song structure. That started to change, which we'll talk about a little bit. Yeah, I also mentioned the musical structure thing. Audio quality was not great yet. And the big thing, I think, is that text prompting is an amazing magic trick. And like, I think everybody who tries it the first time thinks, wow, this is crazy. But it's actually not very useful if you're a musician. Like once you've got over like the excitement and the novelty, it doesn't really help you to like get to the results that you want particularly quickly. So it's clear that these techniques in the future will need different ways of interacting with them. And so that brings me to my recent research, which is addressing some of these deficiencies. What is the end time, by the way, Tom? Is it 6 or 6:15? Okay, good. I don't want to bore everybody, so you can jump out if you need to. Yes, so recent work that I've been doing basically aimed at addressing these deficiencies. So whilst I was at TikTok last year, I started thinking about this problem of like basically interaction, like I just said. So as a musician, or someone who likes to make music at least, I wasn't getting a lot out of these text condition models apart from like sampling material. So it's a bit like crate digging in a charity shop or something for records. Like you can put in a prompt, you can get something back, and then maybe you can chop it up and sample it. But like it's not really directly usable in a normal music production process. So I wanted to come up with a model that was more useful in that process, that would actually like be able to react to the music that you were making and do sensible things. And that's what I made. So, and the way I did this was by reformulating the generative problem. So instead of like taking some conditioning like a text description and just generating music, I instead trained a model that would take some context audio and then produce a sensible musical response to that. And the way that this is done is by taking a data set of music that's in stems, so single instrument form ideally, but it could be mixed down a bit more than that, and then making random submixes from that. So you say, for example, you've got a track that's like bass, drums, guitar, piano, for example. You might randomly pick guitar and bass, mix them together. That becomes your context. And then for the target thing you want to generate, you pick one of the stems that was remaining. And so you just repeat this again and again through the training process, and you get a model that learns how to listen to music and respond. The difficult thing about this is that there's actually not a lot of data sets out there that have music split into stems. You could do stem separation, but then you get into audio quality issues and stuff. So that's kind of the limiting factor to this approach at the moment. But it works, and it sounds pretty good, and I published this at ICASP this year. Given we're short on time, I won't go too much into the architecture. I will rather play you examples. But from a high-level perspective, this is done using a masked language modeling approach, basically, but with some tweaks. If you're interested, then you can read the paper, but let's listen to some examples. So, data set thing here. So, the big data set of multi-stem music that's available out in the world at the moment is called SLAC, which was done by this guy, Ethan Manilow at Magenta, Google Magenta. It's basically general MIDI music. So a caveat that the sound quality of this sounds like general MIDI music, because that's what the data is that we put in. But nevertheless, I think it's obvious that this approach works and responds sensibly. So I think this is quite a nice one. So this is the response that you get if you feed it this particular context audio. So that's not generated, that's the context that you're giving it. And then if you prompt the model to generate a synth, then you get this back. We don't want to hear it on its own, we want to hear it mixed in, right, to see if it makes sense. So let's listen to that. So broadly makes sense. So let's listen to this again with generating drums this time. So the context is like some rhythmic music, but without drums in it. So we prompt the model to make drums. Sounds like drums, right? And mixed together. I like that example. I mean, sound quality is obviously general MIDI, but it's following the rhythm, but it even picks up on the little transition, and you get like a ride cymbal triggered. Like it's following the music, so it works. I would recommend taking a look at this page if you're interested. There's also some live demos from a little live app that we built to use this. It's pretty interesting, I think. So, yeah. Basically, so the end result of this work was a model that could produce pretty good sounding music. Caveat, based on the data set. We invented a new metric to track whether this was actually musically coherent with the context that you were giving it, which you can read more about in the paper as well. I think this shows a way that these models can be taken to be more interesting and more useful in a normal music production process. The big challenge at the moment is data. So there's not a lot of stem separated data out in the world. Certainly not for free. There is paid stuff, and probably if you manage to get in with the major labels, they have incredible archives of this stuff, but publicly there's not a lot. So I'd say continuing this work is predicated on finding like good new data sources. But that's something that I want to do. How are we doing? Okay. So another new piece of work that I have been involved in recently. So this is from actually only a couple of months ago. So this is basically what I was working on since I joined Stability at the end of last year. And the purpose of this work was to basically address the two of the deficiencies that I mentioned in the previous slide. So this is not so much about controllability. This was about, can we scale the context length of one of these models to cover entire tracks? And if we do that, do we get sensible musical structure? And the answer is basically yes. So this graph down here, that probably deserves some explanation. That's taken from the paper. So basically, to decide kind of what our target length that we're going to train our model on, or maximum length we're going to train our model on, we went and analyzed like a representative subset of music metadata from Spotify. So trying to understand like what the length distribution of real world music is. And you can see here, this is basically the cumulative distribution. So if you look at 90 seconds and then read off on the y-axis, that means like 4% of the music is below 90 seconds, or like 200 is about 0.5, like 50% of music is below 200 seconds. So you can see here that 30 seconds, which is musical M or music gen, it doesn't cover anything. 90 seconds, which is the previous version of stable audio, covers only 4% of general music. We wanted to target a much higher percentage, so we settled on 285 seconds, which is 83% of music, which is much better. And the way we went about this, again, I won't go deep into the details because we don't have too much time. I mean, in a way, it's one of these, if you've worked in machine learning for a while, then you'll know that often the solution to a problem is scaling things and pumping it into a transformer, and that was kind of the result here. So what we did was switch from the architecture that was generally used for diffusion models in the past, which is called a U-net. That's something that's like got lots of convolutions in it, lots of upsampling and downsampling. Instead, we use basically a transformer, like a vanilla transformer almost. I mean, in the diffusion context, people call them diffusion transformers, but they are basically the same transformer that you would use for a language model. You're just giving different inputs, and you're asking it to do a different task. So that was one aspect of getting this to work. So use a really big transformer model. The other aspect is that you've got to come up with a latent representation that is compressed enough that you can cover these long time windows without everything becoming like overly computationally intensive and taking ages to train. And we did this also by scaling. So we just we aimed higher in terms of temporal compression than people had previously done in these autoencoders and codec models, and just trained the thing for ages. And if you train it for long enough, then it gets good, even though it's really, really compressed. And from this, we basically got, in terms of published models, state-of-the-art results, we can't really compare to things like Suno because they're not published, and we can't necessarily reproduce the same prompts. Also, they're working with vocals and things like that. But in terms of published models, state-of-the-art results, also good long-form structure, so you end up with music that does actually make sense. Yeah, so basically successful. We addressed we addressed these deficiencies by scaling, which is the classic machine learning result, I think. I can play you a little bit of output from Stable Audio 2. Which one should we play? Do we want the Brazilian tune or the jazz? I quite like the jazz. I'll let it play for a bit longer so you can see that it's not just repeating. Solo in a minute. There we go, there's the guitar. Anyway, so I would recommend listening to these longer tracks. I think it's kind of amazing that just by scaling this stuff, not doing anything really special or particularly clever, you get sensible musical structure. You get little solos, maybe not human quality solos, but like you get stuff happening that makes sense, which is obviously enormously exciting. Yes, and the cool thing to talk about just before we end is that actually I think maybe 5 minutes ago, we released a new model. I wanted to demo it, but I'm not sure everything's up already. That's basically a new model that is based on the same architecture used in Stable Audio 2, but it's trained on a set of CC 0 and CC BY data from Freesound. And this is a fully open weights thing, so this is available for the world to hack and do cool things with, without having to worry about like it being based on stolen data or like all the other kinds of problems that are rife in this world. So this is a little bit different to Stable Audio 2 in that it's more focused. Well, it's a product of its data set, right? So Freesound is a fantastic resource. It's mainly not music, so it's sound effects. It's like short instrumental passages. It's like samples. And so we trained a model that targets basically that kind of domain. So it's generating up to 47 seconds. That doesn't mean that somebody can't take that and fine-tune it to a longer context. I'm sure people are going to be doing that within 24 hours of this going up. But yeah, the base model doesn't do this. And the idea was to build something that's actually useful. Well, okay, part of the idea was to put something out there that people could build on. But the other idea was to make something that is more useful for the production process. So like, well, so not in the way that we talked about with StemGen where it's reacting, but in a way of getting to that sample material quicker. So like you can prompt for like a TB303 acid arpeggio or something, and it's going to write you a pretty good one. You can prompt for like, I don't know, thunderclap on a rainy night in, I don't know, someplace in Britain or something, and it's going to sound, you're going to get something back that sounds basically like that at like full like CD, 44 kilohertz stereo quality. So really excited about this. I think it's going to hopefully lead to lots of interesting new stuff in the community. I would hope so. People usually build cool things when they get access to stuff. Yeah, and you know what? Maybe I can demo it. Let's see if my colleagues have actually pressed the button yet. No, they haven't, so you're going to have to try it later. I'm sorry. That was unfortunate timing. Yes, so there we go. That's what's going on in the world of music generation from my perspective. What's important in the future? Like, what am I thinking about at the moment, personally? A big thing, and I've touched on this a bunch of times, is like, what do we actually want from this technology? Like, what purpose does it fulfill? Because I think we're past the stage now where it's interesting to just do for the sake of it. Like we're into the stage now, like, how do we make the world a better place? My opinion is that that's probably not necessarily always focused on generating full mixed music, right? Because that's, well, for multiple reasons. Like, I'm not sure that the world has a shortage of music. Like, anybody who tries to make music realizes it's impossible to get your stuff heard already. So, like, do we need more music that's devoid of human input? I don't know. But what we do need, and what we would like to do, is to, like, have more people involved in the process of making music and enjoying that, and like putting stuff out there in the world that, has some part of them in. That's my opinion. Like, that's the interesting part. That should be clear also from the things that I've been concentrating on. I think another big thing is personalization. So obviously these models are trained on large amounts of data, but maybe you have a sample library or like a corpus of records that's very idiosyncratic, like your style, and the models can't produce stuff in that style. How do we adapt these models to fit like people's personal aesthetic preferences and make them usable in that context? And then there's a bunch of interesting technical stuff that's coming up. So as we've kind of experienced, transformers solve everything, but a large part of this pipeline for these models is still not based on transformers. So for example, the codecs are usually using convolutions and stuff like this. Can we move to a fully transformer-based pipeline and then get similar scaling gains from doing that, for example? And then the other big thing is going to be making this stuff run quickly. Like huge models running in the cloud are useful for certain things, but if this stuff is going to be like fully democratized and fully integrated in production processes, probably you want it running on your laptop, and you want to be getting answers back or like outputs back not in half an hour, but in like 20 seconds. So that's still going to be a big thing in this area. Yeah, that's basically it. We've got 5 minutes for questions, right? So.